Is 3I Atlas, the interstellar comet now passing through our solar system, an alien artifact? No. Thanks for watching. Oh, we still have some time left. Alright then, welcome to Science and Futurism with Isaac Arthur. I am your aforementioned host, Isaac Arthur. While space, science, and futurism are our main topics here, we spend a lot of time talking about hypothetical aliens, and mostly why alien civilizations are probably very rare, and we probably have this whole galaxy, and likely many more, to ourselves. Normally, I do not like to tackle individual phenomena because there's inevitably very little data. You cannot say for sure what one phenomena is without deeper study, and thus you really shouldn't be saying what it isn't either. However, back when the first interstellar asteroid got found, Oumuamua, I said if we found another I'd talk about it, but until we had a few interstellar asteroids, it was kind of premature, and I got reminded about that recently, so it's time to talk about them. We might as well begin with the name, and 3I indicates the third interstellar object found, Oumuamua being 1I Oumuamua in 2017 and 2I Borisov in 2019, which was less discussed. Astronomers first spotted this object on July 1st, 2025, using the Asteroid Terrestrial Impact Last Alert System, or ATLAS for short. A set of wide-field survey telescopes scan the skies for anything big and fast enough to cause trouble here on Earth. Instead, ATLAS caught something far more intriguing, an object not from Earth's neighborhood at all. Its official designation is C2025N1 ATLAS. The C stands for Comet. 2025N1 tells us it was the first comet discovered in the second half of July 2025, and ATLAS credits the survey that found it. But because it's not bound to the Sun, astronomers gave it a second name, 3I Atlas. The I means interstellar, it's only the third confirmed interstellar object we've ever seen. So you hear people call it 3I Atlas, they're following that convention, third interstellar discovered by Atlas. What makes 3I Atlas fascinating is that it didn't just come streaking through the solar system as a faint rock, it came alive. Almost immediately it showed the characteristic coma and tail of a comet, gas and dust boiling off into space, and unlike most comets we've cataloged, it started doing this while still far from the Sun, over 3 times Earth's orbital distance away. That hints at unusual chemistry, with ices far more volatile than just water leading the show. At the time of discovery, its path revealed a hyperbolic trajectory. It wasn't orbiting the Sun at all, but swinging by once before heading back into interstellar space. Its perihelion, the closest approach to the Sun, will come on October 29, 2025, and Earth will have its closest look in December. We will never get a second chance to observe it unless we send a spacecraft chasing after her. I'd have preferred to write about it in the spring when we had all our data, and SFIA is not a science news channel, and there's folks like Jean-Michel Gaultier, Anton Petrov, and Fraser Cain who do often cover news topics and cover them well, including this one, so there is no rush. But honestly, I do not expect the question of its alien or not to be changed by anything we learn. At the same time, this is a good opportunity to consider whether we, or any other intelligence, might someday hijack interstellar comets and asteroids as spaceships. We'll circle back to that later since it's pretty central to the question of whether 3I Atlas could be an alien vessel, and the short answer there is yes-ish. Comets 101. Now, as a quick refresher, the default orbit of any object bound to a star is elliptical, sometimes nearly circular, sometimes stretched into a long oval. Many comets follow extremely elongated ellipses, swinging close to the Sun, shedding hot gas and dust into bright tails for a few months, then retreating far beyond Neptune or Pluto. Comets are not stable objects. Each time they grow a tail, they are shedding material and will eventually run out. On top of that, a comet's tail behaves like a low-powered rocket exhaust. As ices sublimate, water, ammonia, methane, carbon dioxide, and other volatiles, they vent off into streams, gently pushing the comet onto a slightly new path. The strength of this push depends on both the comet's composition and how close it gets to the Sun, and those factors change from one orbit to the next. Add in gravitational nudges from the planets they occasionally pass by, and comets end up with orbits that can shift and wander quite a bit over time. Now, a very eccentric local comet can get mixed up with an interstellar comet on a hyperbolic trajectory, and that just means its orbit isn't an ellipse, but instead passes by the Sun, picks up speed in the process, and has more speed than the escape velocity from the Sun at that point. It might be a little more or a lot more, and either way it's not returning. This generally means it didn't originate here either. When a random body moves past some other large celestial body, be it a planet, star, or even a black hole, it will gain speed as it nears that body, and lose that same speed when it passes on, but having its trajectory bent toward that body in a hyperbola. On a very rare occasion, this might be a parabola instead, meaning the incoming object gets bent right back around the direction it came from, much the same as most orbits are elliptical, but some are very nearly circular. Now, you can use this for a spaceship to change directions for little to no fuel. You can also steal momentum by accelerating at the right moment using the birth effect, which works better the closer you get to that body. So even though the area a star would inhabit and shine on brightly enough to make a comet tail is much less than a billionth of its overall volume of control, its Hill sphere, mere light minutes instead of a light year, a passing interstellar spaceship is likely to intentionally aim toward a star to steal some more speed, especially if it's unable to pull off truly relativistic speeds using its own engines. Keep this in mind, because it's probably the strongest argument anyone can make for assuming an incoming interstellar comet might be a spaceship. The main alternative idea, that it's actually an alien probe, does not hold up too well, and we'll get to why in a bit. Now, when astronomers confirm a hyperbolic trajectory, that doesn't automatically prove an interstellar origin. It simply means the object is about to have one. A perfectly ordinary comet could skim past Jupiter or Saturn and get its course tweaked, slingshotting it up to escape velocity. But once 3I Atlas's path was carefully plotted, nothing suggested it passed close enough to any planet to get kicked out of the solar system. That leaves only one conclusion. It really did come from the stars. And that makes it alien, though in the more mundane sense of being foreign to our solar system. It might be piloted by bug-eyed green monsters, or far more likely, it's just a lonely shard of rock and ice flung from some other star system by one of a dozen natural but fascinating processes. So we have before us not just another icy rock, but a messenger from another star, carrying clues to alien chemistry, alien worlds, and alien histories. And, like its predecessor, it's already causing debate and excitement about what it means, and whether it might be something more than just a comet. Could it be a spaceship? If you wanted to cross the stars on a budget, a comet or asteroid would make a pretty tempting option for a spaceship. For one, it's already got the bulk of what you need: tons of shielding against radiation, reservoirs of ice for water, air, and fuel, and a solid mass to bolster machinery into, as well as to extract minerals from to repair and replenish your equipment. Hollow out the core, add some habitats and engines, and you got yourself an interstellar arc disguised as an ordinary comet. But on the outside, it wouldn't look all that different from a natural body like 3I Atlas. Even without engines, there's another trick in the playbook: gravitational assists. We've used them for decades to sling probes like Voyager and New Horizons across the solar system. A ship can dive close to a planet, borrow some of its momentum, and come away with a speed boost relative to the Sun, or even the galaxy. Pair that with the birth effect, firing your engines when you're at the fastest point near the massive body, and you get far more bang for your buck. Here's why. If you fall in toward a planet, you naturally speed up as you approach, and then slow back down as you climb away, returning the same velocity you started with. Your engines, however, deliver the same amount of delta V no matter where you fire them. So if you've got 10 km per second of delta V, equal to about 50 megajoules per kilogram, and you fire that while cruising at 10 km per second, you'll simply jump to 20 km per second. That's 200 megajoules per kilogram, 4 times the original energy. But if instead you fall toward a planet first, you might accelerate to 30 km per second at the bottom of the dive, temporarily holding an extra 4 to 50 megajoules per kilogram. Fire your engines there, adding that same 10 km per second of delta V, and you jump to 40 km per second, a whopping 800 megajoules per kilogram. On the way back out, you lose the borrowed 4 to 50 megajoules, but you still keep 350, leaving you with a final speed of 27 km per second. In effect, your engines only supplied 10 km per second, but gravity gifted you an extra 7 km per second for free. and the closer you dive toward a massive body, the bigger that free bonus can become. Around black holes can be truly incredible, so you can get quite close without being burnt by a star. If you are a comet though, your proximity is even more limited since you are evaporating matter, and we see an interstellar comet diving toward the sun. It raises the thought, what if it isn't a comet at all, but a ship taking advantage of the same tricks we would? That's really the strongest argument for thinking of an object like 3i Atlas might be a vessel. If we were building interstellar craft ourselves, that's the sort of trajectory we would plot, but there's a big difference between plausible and likely. There is no sign that Atlas is being steered, no indication of artificial structure, and no behavior that cannot be explained by perfectly ordinary physics. So could an interstellar comet be a spaceship? Again, yes-ish. The idea works in principle. Comets could make a convenient natural starship. When it comes to 3i Atlas, there's nothing to suggest it's being used that way. Why is it probably, and almost certainly, no? Well, first off, you wouldn't build your ship to be covered in volatiles, an amazing rocket fuel, then let them casually boil off into space in a fairly unpredictable and low-yield way. You cover yourself with a skin and use any energy you had to vaporize that matter as a good rocket flame or ion drive and get way more bang for your buck. You'd also probably massively expand your cross-section as you extended a solar sail out to absorb energy and deflect incoming light and solar wind to your advantage. If you're not doing that, then you don't have very good engineers. Now, the ship could be broken, but whenever we start contemplating Fermi paradox solutions or candidate phenomena that only work if they are malfunctioning, we're opening a big can of worms. When we talk about potential alien technosensors, especially ancient ones, it's fair to assume some might not be working optimally anymore. The key word though is some. We should always expect multiple technosensors. You might only spot one from far away, perhaps because it's the brightest or most obvious, but closer scrutiny should always reveal more. A house or a human city produces dozens of technosensors, from lights to heat to waste. Even a ruined house or city still leaves behind plenty of traces. Your porch light might be the easiest to see from a distance, and might even be mistaken for something natural. Once you look closer, it becomes obvious you're dealing with technology. At the time I'm writing this, I'm in the hills of Kentucky with my wife and kids. Obviously I'm back now as I record this, waiting to go explore Mammoth Cave tomorrow, and we're staying in a rural cabin. I'm horrible at vacation, so of course I'm working, but travel always puts me in the mood to write, and writing is my favorite part of this job, and for me at least, quite relaxing. And while I have around 30 scripts sitting around these days, backlogged on being recorded and turned into videos, which will probably fast-track this one around. Anyway, this very modern log cabin has high-speed internet, running water, a porch light, and dozens of technosensors that separate from the trees around it. On the way here though, we passed an abandoned trailer, and even the remnants of an old shed or log cabin. Those wouldn't have many active technosensors anymore, but they still left clues. Gravel driveways, metal hinges, nails, windows, broken bottles or soda cans. Now that's the key point when evaluating potential technological phenomena. Any genuine technosensor should come bundled with others. Some harder to spot, perhaps, but clear enough once you start paying attention. We are paying attention now, as we did with Oumuamua, and I haven't heard of any other anomalies this comet has that stick out as technosensors. We may find more when it makes the closest approach, as you get more time to study it, but for now, here are some that make it stick out compared to other comets at least. The Real Anomalies. Now, 3i Atlas does have some features that set apart from most comets we've seen before. The one getting the most attention is its chemistry. Observations suggest its coma is dominated by carbon dioxide, with CO2 outnumbering water vapor by nearly 8 to 1. That's an odd mix compared to water-heavy comets we usually encounter, and hints that it formed in a much colder and more distant part of its home system. Another curiosity comes from polarization studies, which measure how sunlight scatters out the dust in a comet's coma. We had a paper out on it last week, and it piqued my curiosity more than a lot of the other prior discussion on this matter. Here's why. Normally when light reflects or scatters off dust particles, the waves of that light become polarized in predictable ways. For most comets, you see what's called a negative polarization branch, at very small phase angles. That's the angle between the Sun, the comet, and our telescopes. In simpler terms, when the comet is nearly opposite the Sun in the sky, the scattered light tends to get slightly depolarized before flipping back to positive polarization at larger angles. What makes 3i Atlas stand out is that this negative polarization dip is much deeper and sharper than usual, and the angle where it flips back is shifted compared to solar system comets. That suggests the dust grains around it are different size, structure, composition, or some other factor. They may be fluffier, more porous aggregates of fine particles, or they might have unusual surface coatings that change how they scatter light. This isn't just an academic oddity. Polarization studies are one of the few tools we have to remotely probe the microscopic texture of an alien dust. If 3i Atlas's grains really are structured differently, that makes them a valuable sample of geology from the star system, a reminder that even something as subtle as how light is twisted and scattered can carry fingerprints of a world born light years away. The comet also showed early activity, with water signatures being detected while it was still over 3 astronomical units from the Sun. Most comets don't really start boiling water off until they're much closer. Indeed, the frost line, or water-ice line for our solar system, is about 2.7 AU, around where Ceres is. You wouldn't expect to see much sublimation beyond this, or even a bit closer, same as you don't get a lot of ice melting when it's a couple degrees above freezing. Best hypothesis at the moment is that it might mean that 3i Atlas has big icy grains in its coma that evaporate slowly, or particularly active spots on its nucleus. Remember, by the way, that scientists not being certain why something is happening does not particularly imply it's strange and artificial. In point of fact, all things being equal, early mass loss from an object will generally indicate it is not artificial, since you wouldn't want your spaceship to be losing mass except as propellant, which is not the case here. It also decreases its stealthiness by making it visible earlier, which would counterindicate it being a probe, but back to that in a moment. Finally, its orbit itself is a little eyebrow-raising, retrograde, but aligned only about 5 degrees off the ecliptic plane. Things orbit near our ecliptic in this solar system because the early solar system formed as one big disk, spinning in the same direction and clumped into pieces. There's nothing prohibiting anything from coming in that way. It's preferable for a probe, for instance, but a random object from an extrasolar source would come in from a random direction, and only a small percent of those directions would be in that ecliptic plane. That's close enough to be surprising, though likely coincidence. A 10-degree wedge out of 360, around 3% likelihood, so improbable but not freakish. Thus it makes for a neat reminder that even random visitors can come in on familiar-looking paths. None of these traits scream alien artifact. They are unusual, yes, but unusual is exactly what you expect from a chunk of ice and rock forged around another star. We often imagine humanity's future in space in centuries to come, but rarely stop to notice how deeply our own society depends on the simple fact that we live about a century. Everything from schools to pensions, from child care to retirement, basic family structure and society focus is structured around those limits. Change the lifespan, and you can change the very fabric of the economy. That's the idea behind my latest monthly exclusive episode, The Economics of Immortality. What happens when time itself, the rarest commodity in the universe, becomes abundant? Whether through medical nanotech, gene editing, or mind uploading, immortality could transform how we work, learn, raise families, and govern, and each method opens the door to a different pathway. It's not just about living longer, it's about how whole civilizations might be reshaped when generations never end. That's out now on Nebula, the largest creator-owned streaming platform, where every episode of SFIA is available early and ad-free, and where I've been posting full-length exclusives like this one every month for years, along with extended editions, bonus content, and amazing originals from other creators. These are exclusive and larger projects made by our creators for Nebula. Get a lifetime membership, normally $500, for just $300 by using my link, go.nebula.tv/IsaacArthur, and unlock everything forever. Or get an annual plan for 40% off, $36 a year. That's 12 months for the price of 7. Scan the QR code or click the link below to start watching now. Head to go.nebula.tv/IsaacArthur to join and start watching exclusive content like The Economics of Immortality. Why it is not a probe. Now, there's a difference between a natural body that could be repurposed into a ship and an object deliberately built or sent as a probe. A probe implies intention, navigation systems, instruments for gathering data, a way to transmit that data back, and usually some kind of maneuvering capability to steer itself. None of that is in evidence here. As with any alien scenario, we also have to consider motivations and goals. If the builders don't want us to see their probe, then this is a terrible design. A bright, gassy comet tail is not exactly stealthy. Never draw attention to something you're trying to hide, even if it would look like it's camouflaged. On the other hand, maybe they did want us to see it, in which case we should expect it to unfurl massive solar sails any moment now and start blasting us with radio waves, or maybe even flashing a semaphore of light across the heavens. In the absence of that, the only remaining options are that they don't care if it's noticed, don't expect anyone around to notice, or whatever stealth or broadcast system it once had is now broken. It would seem unlikely they wouldn't care. They are not stupid, so they would hypothesize another intelligence could be present and consider the consequences of getting spotted. Same concept. You do not need to send some massive probe to figure out our solar system as a planet with life on it. Technosignatures would be new, but biosignatures would be billions of years old. That comet tail, incidentally, would be an amazingly handy way to show something by running a giant projector into it. I can think of easier ways to get seen, but a cometary billboard is admittedly a pretty awesome and viable approach. The behavior of 3i Atlas matches what we expect from cometary outgassing, and where it deviates from the norm, it isn't anything that would seem required for a probe and thus would tend to indicate bad engineering by letting an anomaly creep in that didn't need to be there, and thus might draw attention. Its brightness changes, it has faint trajectory deviations, even its early water release. All these can be explained as sunlight boiling off ices. If this were a probe, we would expect to see tightly controlled course corrections, or at least something that looked like engineered thrust, not random jets firing in unpredictable directions. A real probe would also need to conserve mass and power. By contrast, 3i Atlas is shedding its volatiles freely and becoming more conspicuous the closer it gets. That makes sense for a natural comet, but not for a scout trying to operate discreetly. The loss of mass is wasteful, the visibility is counterproductive, and both point strongly away from design. Speaking of mass, we haven't been able to narrow it down very much yet. On the low end, 3i Atlas could be around 10 megatons, about the mass of 100 aircraft carriers. On the high end, it might be closer to 100,000 megatons, which would be like 1 million carriers. That's a pretty hefty probe, considering ours usually weigh in at something like 10 tons, not 10 megatons, let alone 100,000. And remember, you'd have to accelerate all that mass in the first place. It is hard to imagine that it were truly a probe of that scale. It wouldn't be packed with redundancies, making the idea of it just limping along broken seem pretty dubious. And if efficiency mattered, you'd think they'd use something 100th the mass, moving 10 times faster, or even just 100th the mass, given that an actual telescope in that mass range could probably achieve useful resolution on an exoplanet from light years away and wouldn't need to be moving, fast or slow. High speeds limit the time for close-up observations and reduce how many slingshot maneuvers you can pull off to skim by other worlds. Still, you could send it in fast and use the Oberth effect in reverse, slowing down instead of speeding up. Coming in along our ecliptic would be a smart choice. It could have arranged to pass Jupiter or Saturn to shed velocity, and timing that encounter would mean delaying its arrival by only a few years, in a voyage that would have been several thousand years even from our nearest neighboring systems, none of which realistically house civilizations or major surface life biosignatures. Near or far, that's a trivial delay of launch for an advantageous encounter to save fuel, and makes it look like a local comet that had been perturbed into a hyperbolic escape path. Instead, what we actually see is a body already on a clean hyperbolic trajectory, without having brushed near any of the giants. Again, that's why we think it's interstellar in the first place. That strongly suggests it's truly interstellar and natural, and not the clever masquerade of an alien probe. Finally, again, we appeal to multiplicity. If this were a probe, we would expect to carry a suite of technosignatures, radio transmission, optical beacons, or unusual infrared outputs, even weird reflections in albedo. None have been detected. That absence is not proof, but it's consistent with 3i Atlas being just what it looks like. Comet. So while a comet can in principle be hijacked into a ship, 3i Atlas shows none of the features we'd expect of a purpose-built probe. It's way too big, moving too chaotically, wasting too much material, and producing no signals. In short, the probe hypothesis doesn't fit the data. Why this matters anyway. Even if 3i Atlas isn't a spaceship or a probe, it still matters enormously. Each interstellar object that wanders into our neighborhood is effectively a free sample from another solar system. We can't send spacecraft to other stars, but once in a while, their debris comes to us. That gives us a chance to study alien chemistry directly. What ices, gases, and dust grains condensed around some other star billions of years ago. By comparing those ingredients to what we see in our own comets, we can start to understand how similar or different planetary systems really are. Is water always dominant, or do some systems produce more carbon dioxide, methane, or exotic ices? Do the dust grains always form in compact particles, or can they be loose and fluffy aggregates like the ones 3i Atlas seems to carry? Each new visitor gives us another data point in answering those questions. It also encourages us to ask how we would make a probe, how we would make one that we thought needed to stealth its way into an alien civilization, and we might consider making an interstellar ship this way, something we deep dived in our episode on making asteroids into interstellar ships. In the end, 3i Atlas is almost certainly just ice and rock, but in its passing we are reminded that the galaxy is full of stories written in stone and dust and ice, waiting for us to learn how to read them, and perhaps one day to write them too, as we reach out into the galaxy ourselves.